let's talk from a 3D standpoint. So let's talk about the center of gravity first. So center of gravity. And first we have to make a few observations. Before I make these observations, let me introduce you to what's called the mechanics potato here. So this potato is a random shape that is floating in random space, and it is not very much defined except for a few things that I will call out for you in a second. But notice that we have also a randomly oriented coordinate system, an origin here, and that behaves random to this potato. However, later on you pick that, of course, in a very smart way. But right now our goal is to generalize it. So the first observation that I have to make about this potato, it's pretty much any physical body. So any body is composed of multiple components, and these components here, I call them dW. W for weight and D for super tiny, super small, right? And because it's super tiny, super small, there's infinite amount of them. So my first observation here is that any physical body is composed of an infinite amount or an infinite number of tiny particles, right? Of tiny particles. And those tiny particles, in mathematical sense, they are of differential size. So differential size again stands for dW. So dW stands for tiny, and W stands for weight in this case, because we're talking about the center of gravity. So that's our first observation. The next observation comes also from this picture here, and we see that this dW, which of course exists many, many times, but dW has a distance to the origin of the coordinate system. And this distance is not randomly named like this. It is actually called x tilde, y tilde, and z tilde in the respective coordinate direction. But please note that it's a tilde. So the dW has a specific distance, which is x tilde, y tilde, and z tilde. While this coordinate origin is randomly chosen and the potato is randomly in space here, we can say that any random particle has these three distances. So each particle has a distance to the origin is my next observation. So each particle dW has a specific distance to the coordinate origin. And that we call x tilde, y tilde, and z tilde. So far, only observations here. One last thing, of course, I just want to emphasize again, is that each particle also has weight, right? So it's not weightless, it has weight, it's just super tiny in this case. And now we can pretty much complete our fill in the blank here on the bottom. So x tilde is the distance between the particle and the coordinate origin in the x direction. So distance between particle, and that's the super tiny particle, so dW, distance between particle and coordinate origin. And in this case, it's in the x direction. In the x direction. And of course, I have the same for the other directions. So I have here for in y direction. And I have in z direction. So just to be clear, here I have my z direction, then here I have my y direction, and here I have my x direction. And again, the term you want to memorize is the tilde, right? Or the symbol you want to memorize is the tilde. And let's talk about the distance for one more second here. So it's not the distance to anywhere actually of dw. So dw technically has a centroid too, but it's so tiny we don't really care about it. So we just consider dw like an infinitely small point, and therefore it just goes from that point to the coordinate origin. And with that said, we now have the observation of dw, and we can move on to further observe the potato. So let's go to the next page. And here I see the very same potato, but with a little bit different representation. So let's make some observations first. Again, the potato is given here in the random coordinate system, but notice that now I'm not dealing with dw anymore. What's shown here is w, which is the total weight of the potato that passes through a point called G, and that is the center of gravity. So let's write that down. Center of gravity. And another observation that I can make now is that the center of gravity now is not given with x tilde, y tilde, and z tilde anymore, but it's given with x bar. So x bar, y bar, and z bar. And that is not random here. So that defines the distance from the coordinate origin to the point G. So two things I observe in this picture. I have the total weight, right? So we'll write down an observation there, and that is the resultant force of the particle system. So the resultant force of the particle system is the total weight of the potato, is the total weight. But a mathematician would never say it that way. A mathematician would probably say that W, which is given in the picture that you see here, is equal to the summation. And if we have infinite small particles, then we need to use the fancy way to sum. So we're going to use the integral. So the summation of all dw's. And that is a formula that will help us to understand what's going on later on when we further derive this. For now, it's just an observation. So the total weight is the summation of the tiny particles. And that then is passing through W, as you can see here in the picture. So here, W is passing through G, I should say. And let me give you an analogy here the best way I can without being in the classroom together. So I can think of a seesaw on a playground, and I can put a student here, and if I have a student with the same weight on the other side and they both have the same lever arm, then they balance out, and then they would balance about this point. So in a very abstract sense, this would be G as well, because the potato is doing exactly the same thing. So if you poke a needle into G here, then everything on the left side balances everything on the right side. And that's the same what you experience on a playground if you sit on a seesaw with somebody who has the same weight as you. So that is what the center of gravity is really about. Now let's notice another thing, and that is how G is represented here. It is given with these distances here, x bar, y bar, and z bar. So I need to write that down as well. I need to memorize that the distance, so distance between G and the coordinate origin is represented by x bar, y bar, and z bar. And one little side note, I usually would ask you this in class normally, but here I can't get your feedback. So usually I ask my students how many x tildes exist and how many x bars exist. So x tilde we discussed on the previous page. Now we're talking about x bar. So what we would come down to in the class is x tilde exist infinite times. Whereas x bar exists only once. And of course that's true for the other directions too, y and z. So I want you to understand the difference here that we're talking about right now. So this x bar defines the distance between the origin and the center of gravity. And because the center of gravity only exists once in the potato, that also exists only once. Whereas if you look at x tilde, it was the distance between the coordinate origin and each individual particle. So that would exist infinite times as well. Last observation to be written down here is what is W now? So W is the total weight of the body. So W here is the total weight of physical body that passes through the center of gravity. And that takes us to the definition of the center of gravity. Just before I go there, let's remind us that this is a single point, right? Single point, meaning it only exists once for each potato. But now we're ready to talk about the definition of the center of gravity. So let's do that next. Let me zoom out. And let us look at this potato here. Now you see the previous two pictures combined. This is nothing new, just a little bit more convoluted because we're having both here. We have dW here. There's also a dV because this is technically a small volume as well. But we're talking about weight currently. So there's the dW, which this exists many times in here. There's many x tildes, y tildes, and z tildes, but there's also the center of gravity. And that has the distance to the origin as well. And that is defined by x bar, y bar, and z bar, which only exist once. We already talked about that, or we discussed that already. So now the way the center of gravity is defined, right, is that whatever point in space you choose, let's say you choose the origin of the coordinate system, there is actually a weight times a lever arm, right? So in the x direction, it would be W times x bar. And that would create the equivalent moment as each individual particle times its distance. And again, here you see only one of them, but imagine for a moment that the entire potato is made from only two dWs. Then you would say that dW1 times x tilde 1 plus dW2 times x tilde 2 must be equal to the W times x bar. And that is kind of the definition, right? So I'm going to write that down here for you on the bottom for now. So x bar times W is equal to the sum of, so the sum again is infinite, x tilde dW. So, and I say that again because that's difficult to digest sometimes for a beginner. So if the potato were made from only two individual particles, then you had particle 1 times its distance, particle 2 times its distance would be equal to the total weight of the two particles times its distance to the origin. And that's really what the formula here says. And so let's write that down in words just for your definition. So the sum of the moments of all particles, the sum of the moments of all individual particles and their distance, right? Is equivalent to g times its distance, or to the total weight, multiplied by its distance to the origin in our case. But let me tell you, it actually doesn't matter to which point. This is true anywhere in space. So instead of choosing the coordinate origin here, I could also pick this point here, which, like, it could be any point in space. And as long as I fulfill that let's color code it, that the sum of the moments of all individual particles and their distance, right? So that is this component here. And of course the sum is really, so let me box that. So that is the sum here. And then the individual particles is this component. So that would be the individual particle. And then last but not least, I have x tilde here. So let me code that like this. And that is equivalent to the total weight, which would be this component, and then multiplied by its own distance. So its distance, which would be that component. And so now you know that the balance is given, right? So this is nothing else than moment equilibrium that you have learned before. So in fact, let me write that down here. So this is effectively the moment equilibrium. Or in other words, it's the sum of the moments being equal to 0. That's exactly what that equation says, except it is looking a little bit convoluted or a little bit different than what we've dealt with before. And if you remember from the beginning of our lecture, where we're going with this, then you know that we are actually always be looking for x bar, right? So x bar is what the engineer will calculate, because the engineer wants to know, hey, where is that centroid actually located? And to get that, all I have to do is rearrange this formula. I have to divide the right side by w. However, before I do that, I will actually represent w here again, as we already done before. So I can also write that x tilde times the integration of all particles is equal to the integration of x tilde dw. And all I've done now is I kind of wrote my total weight as the sum of all the individual particles. And now, last but not least, what do I have to do to get my x bar? To get x bar, all I have to do is rearrange the system, and I would end up with a formula that looks like this: x tilde dw divided by the integration of dw. And this is a formula you do want to remember for sure. As I will show you in a second, it will come over and over and over again in different forms. But I spent some time here to derive this formula, because it is a formula that shows up in many different fashions from now on. And you need to understand where that's coming from. Here you understand that it's coming from weight. Later on we'll do it for volume, for mass, and for areas. But the actual formula will always stay the same. You will always see an x tilde, you will always see an x bar, you will always see an integration sign, you will always see an integration sign. What you won't see probably is a dw all the time. So this can be replaced by other things, as you will see in just a second. To be complete here, let me clarify that I can also do this for all the other directions. So for the y bar, I would just deal with the same formula, just with y tilde dw divided by dw. And for z bar, I would be interested in finding the z tilde dw divided by the integration of all dw's. And so that's the first clue that this formula, or the shape of this formula, or the form of the formula, is so important, because you see it works in all directions. And in just a second now, I will actually show you that it also applies to the center of mass and the centroid and so on. But for now, we understand that this is the formula that we need to memorize, and we understand where it's coming from. So I derived this here from the top for you. And what we need to understand to get to this point is that we have a balancing equation here, so the sum of the moments. And for now, I can just tell you that any point in space needs to balance like this equation says. We are just choosing to do it over the origin, because that will clearly define our x bar for us. And that is what we as engineers will be interested in. So that concludes the center of gravity. And now I will show you very quickly how this applies to the center of mass and the centroid.